Okay, we might be back. Not sure yet. Everything is slow today. Like even slower than normal. Still loading. Okay. So the things are so slow today. Yes. Back to solving equations. And we were at the matrix decomposition in LU form, in lower and upper triangular form. And we wanted to verify. We have import, numpy, my keyword is working beautifully. Because the laptop is a little bit slow. I don't know what is going on here. It's numpy. Wait. So I need to import numpy, of course, and I need to define my matrix LU as numpy dot. What do I do? Matrix or array? I can use matrix, right? 0.4, 1, then 1 and 0, everything in a nested list. It takes a second to verify. Looks like the matrix just said we want to have, and then actually this is the upper. Is it? Is it the upper or the lower? Maybe they're diagonal? It was the lower. So mysterious, right? Where's the lower triangle? I just see two upper triangles. Where is it? Where? Okay, so now two matrices, right? Important for us now is we have different ones, and when we multiply them, we actually see, yes, we get 2, 3, 5, 4. So what do we do? Ln times um, is that correct or not? No. Oh, it is correct. Why is this correct? Everybody pay attention. So here I have matrix multiplication, right? Ln times um. And we said, don't use the multiplication sign. You get weird results. Remember? Element-wise. But here it's correct because I define Lm as matrix and not as right? So that if you go back here, right, change this to array, then it makes sense. More array. If I can push a button, I need to wait a second. I don't know what's. So this would be element-wise definition, multiplication of which. The cool thing just died on me. Okay. So that would be wrong here, of course, right? So be careful, matrix array, and then if you have with array, you need to have the sign for proper multiplication. Important is, yes, we get 2, 3, 5, 4. What we need to understand is that actually when we flip around the row and the column in this matrix, this will be lower lower triangular matrix. And we will show that later with a permutation matrix that we multiply in front. Okay, but so just to point you to the right position, P here in the documentation is the permutation matrix. So what's the key idea? So the basic idea of finding the solution vector x is to bring a matrix in diagonal or triangular form. So why is it so good to have a triangular form? Because when I have a triangular form, I know that the first component solution in this example here, that if I just take this matrix, would be 1.4, right? And if I have that value for like x2, I know what to do with 4 here multiplied with 1.4 to find the value for x1. You have done this in high school, and you call this, I don't know how you call this because your high school was in Chinese and not in English. But when I translate from my high school into English, it would be solving through elimination. Hmm? Okay. So far, so good. Here's an example, right? Think back to your high school math. Shall we do this comparison again? My high school against your high school? I think that was like 10th grade for me. That's right. You bring this in matrix form and then you form, basically, how do we do this? You can do this together, right? With my high school. You've done it at high school, it must be easy at university. Okay. So what would you do here to solve this? If you take this and you add a second equation and you add it to the first equation, you get 3x, the y cancels out, you get minus 3z, right? But when you subtract it 2 times from the first equation, you get 2x minus 2x, and then y plus 2y, so that would be 3y, and then 2 minus 2z plus 2z, right? So you would see that y equals 1. Right? So you take equation 2 and you add it twice, so you subtract it twice from equation 1. Now that is elimination. Right, and if you would bring this in matrix form, right, you would also see that in the triangular shape, one variable cancels out completely. We can basically read off the values. Okay, so at home you can try to solve this system equation but through elimination, right, in matrix form. But through elimination works and then in matrix form the other time. So back to our topic. Lower upper triangulation. And let me check here first. This one is not working, right? Is it? Oh, 10 people watched it. Let's see, this seems to be all right. Yes, there we go. Okay. So lower upper decomposition. Remember, we always start now with a system of linear equations where we have a matrix A. There is a lot of coefficients that come from the problem setup. Then we have a vector x, that's the solution we want to get, and then we have a value vector b. Now we are going to rewrite our matrix L in form of L times U, which basically after substitution gives L U x equal b. The next trick we do is we look into one part of the equation and we say U times x equal y. So y is just another variable, it's not a function, just a variable, and we substitute for u, for u x y. So our problem then simplifies to a lower triangular matrix times y equals b. But because L will be in a triangular form, from this point we can easily read the values of the solution for one part and further get the values for u, and so reconstruct our full solution of x. That's the idea. Somebody implemented it for us. Today we will see how to use it and then compare it to our other solution approaches. So let's see. Now we work with Python. So we have a matrix A for 5, 5, 4, 8, 3. Then we have a vector B, 3, 4. We check that everything is implemented correctly. To make sure that we find the correct solutions, we first will get the solution with an algorithm we trust already. What we do there is we create the inverse of A, multiply this with B to get our solution vector X. Now, do you remember where linear algebra comes from? How do we import this? Was it like this? No? Was it like this? Maybe, right? So from NumPy, we import the submodule linear algebra that allows us to compute the inverse of the matrix, like numerically. Right? So when we do this, we get two numbers because we have a two-component solution vector. Component 1 will be 0.41, the other one will be 0.235. Now, we look into how to get the lower upper decomposition. And in SciPy, we have a dedicated method for this called LU. So we import SciPy, and then SciPy also has a linear algebra component. From there, we call LU. Let's see. So we import. So it's there. If we want to have the hell, we can use the hell build method in Python and see what LU can do for us. So LU performs the decomposition of A, P, L, U. So P is a permutation matrix. Do you know what's a permutation? So when you have like a list of values A, B, C, and you swap the position of two components, that's a permutation. So far, so good. What does the function take? The function takes A, for which we are supposed to find the decomposition. We have, that's important, a few other variables. For example, permute L, it's a Boolean, perform the multiplication P times L, or do not provide the permutation. Override A as false, whether to override data A, meaning we take a matrix and then we override the data in place. Check finite, whether to check that the input matrix contains only finite numbers. So far, so good. So what's an infinite number? Infinite number, infinite, finite, infinite, infinity, right? So far, so good. Now the return values will be our permutation matrix, our lower and upper triangular matrix. There are a few examples which you can explore yourself, but we try our example. Now, how do I call the function, right? The algebra, which I just imported from SciPy. then LU, and then A. You need to be very, very careful because I imported linear algebra from NumPy over here, right? Where is it? Here. Now I import SciPy and see, and then I ask, hey, what is SciPy linear algebra? I think I also should be possible to form SciPy. Import linear algebra. What do you think? Seems to work as well, right? But this is somewhat dangerous now because every time I execute this code block or the other, I override my linear algebra. So far, so good. Do you understand the problem? I have two different modules. They use the same name for one of their packages, submodules. So to keep track on what I do, you actually need to either know where to load which module, you give it a different name, or you try not to load two submodules with the same name, right? Which is basically giving the same different name. We have the same situation with the cosine function in NumPy and SciPy, right? But there I could really cause some trouble. Now here, I actually could do the trick. It's just not a very clean implementation in the sense. So if you write report and then you say you used SciPy, but you loaded NumPy, technically well, it is definitely a mistake, right? So you need to be very clear what you do with. So let's look into L. L is this, very good. U is this, very good. So we see already we have at least now one triangular matrix. So that's the other one is also a triangular matrix. Yes, no, maybe. This is a diagonal. Everything above the diagonal is a zero. So that must be our lower triangular matrix. In example U, we have a diagonal, 8 and 2.125. Everything above the triangle has, well, sorry, everything below the diagonal is a zero, so that must be the upper triangular matrix. Now, the big question, what is this mysterious P matrix? Oh, that is just 0 and zeros and ones. Huh, interesting, no? So fast. So when I now take L and you multiply with U, I should get back my matrix, right? So I get 8, 3, 5, 4. Is that what I put in? As A. 5, 4, 8, 3. It's not the same. Do you see this? For matrix A, this is not the same. It's a problem or no problem? It's not a real problem because if you remember, actually, the decomposition of this matrix of this method is P times L times U. So I get my lower and upper triangular matrix. I always can swap lines and rows of a matrix, right? So I want to restore the full form of A. What I actually need to do is P multiplied by L multiplied by L. n. So very good. So now I have restored my matrix 5, 4, 8, 3. Right. And the same is basically now given here as examples down the road. We have 5 more minutes to the break. So what we could do is another example here. So do you remember our matrix LM, the matrix UM? When I take those and I have LM times UM, I get the original problem that was given, right? Now from linear algebra, from LU, let's see, I get my permutation matrix, my lower and my upper triangular matrix. Look, yes, that work. Now when we check L, when we check U, basically get as it should be, right? Now the problem is that in lower and upper triangular form, LL times MM, that's always better, UU, did I do a mistake now? LU, B. Ah, it's the same, very good. So important to remember is lower upper triangular matrix decomposition algorithm, yes, provides us lower and upper triangular, but because we always can swap a line and a row in a system of equations, we must remember to reproduce the full solution to get the permutation matrix. Sounds good? If there are no questions, we have a break. Right. After the break, we finish this part and go to the next chapter, which would be chapter 5.